Good morning and welcome to today's session. In this session we are going to discuss one of the important mixture model, namely Gaussian mixture models. Today's agenda: first of all, we discuss some preliminaries related to normal distribution or Gaussian distribution, then formal definition of this Gaussian distribution in the case of vector form, then derivation of GMM, that is actually the probability density function for the mixture Gaussian model, and finally its applications. Our goal is to generate a most normal object in considering all aspects. We need normal in all aspects. As an analogy, you think about fixing your marriage. If you are an extremist, it creates problems. Your partner should be normal in all aspects. Suppose you expect a very good smile from your partner. If she or he is always smiling, that creates problem. You expect your partner to be very much interactive. If she is over interactive, it creates problem. And also you want your partner to be jovial. If he or she is extremely jovial, that creates problem. That means we expect a mixture model which is normal in all aspects. That's all. So the preliminaries related to normal distribution. A Gaussian distribution can be denoted like this: n of mu sigma square, where mu is the mean and sigma square is the variance. And sometimes we say that the normal distribution is a biparameter distribution. In order to derive the PDF of this distribution, we need only the mean and standard deviation, and it is symmetric. Is a symmetric distribution with mean is equal to median is equal to mode. That is one of the most important and nice property for this normal distribution. All three measures of center tendency should be equal, and it is also bell shaped. The probability density function is bell shaped and is fully determined by its mean and variance. I already told it. Now the PDF of normal variate is given by f of x is equal to 1 by root of 2 pi sigma square. This sigma is inside this root, 1 by root of 2 pi sigma e raised to minus of x minus mu the whole square by 2 sigma square. All this expression is in the power of e. So this expression gives a bell-shaped structure to this Gaussian distribution. Now we are going to discuss the standard normal distribution, the most used probability distribution in statistics. Now this is the shape of this normal distribution. Now look into this shape. The center point, the center vertical line passes through the mean, and this distribution is symmetrical about this mean. That means the area under this graph is 50% to the left and 50% to the right. Now look into this 1 sigma standard deviation to the right and left. Within this 1 sigma standard deviation, there are 68.3% of data items will lie. Now think the next limit, that is 2 sigma standard deviation. We take minus 2 sigma to the left, that is up to minus 2 sigma, and we take 2 sigma to the right, that is up to 2 sigma from this mu. It contains 95.5% of the data items, and moreover in 3 sigma standard deviation, that means 3 sigma to the left and 3 sigma to the right, under this area it contains 99.7% of the data points. That is an interesting calculation related to normal distribution. All these ideas will be encapsulated within this distribution, the most desirable one. See, in the case of normal distribution, we have all the three measures of center tendencies: mean, median and mode are same. And so it is a single mode model distribution. Single mode distribution means it has only one peak, and symmetry about the mean and all these ranges etc. will help us to identify and also calculate the probabilities and calculate the number of samples having a particular probability, etc. So the most useful distribution is normal distribution because it is completely predictable distribution. We can make use of the distribution to the fullest extent. Okay, and also the usual statistics or the conventional statistics is actually make use of the normal distribution in all the theories, because there is a center limit theorem. It says that if we have a large number of samples, then the sequence of partial sum of the sample mean that samples create a normal distribution. Like the proverb says, all roads leads to Rome. All distribution becomes normal distribution if the sample size is very large. This is the basic idea, and we can use this idea in the case of our base posterior. In the case of prior distributions, the selection of prior distribution or our belief distribution, we can choose any distribution, no problem. If it contains more data points, automatically that distribution will become this normal distribution. This is the basic idea that we are using in our Fisher statistics or conventional statistics. Okay, now we define the multi-Gaussian distribution. That means if we have a vector form X, it contains many, here I choose k components, then we are going to represent a vector form of the Gaussian distribution, the Gaussian probability density function, that is 1 by 2 pi the whole raised to k by 2. See, this all is similar to root of 2 pi. In the case of root of 2 pi, I am using the k clusters or k elements in that vectors. So 2 pi raised to k by 2, and this modulus sigma raised to half. This sigma is actually covariance matrix, and modulus sigma raised to half gives the root of that covariance matrix. Then e raised to minus half into, in the original distribution we have 1 by minus 1 by 2 into x minus mu the whole square by sigma square. In order to make it in a matrix product, we split it like this: x minus mu into sigma raised to minus 1. The sigma raised to minus 1 is actually 1 by sigma. 1 by sigma, this capital sigma is variance. That variance is actually sigma square. So sigma raised to minus 1 is simply a matrix representation. X minus mu into sigma raised to minus 1 into x minus mu or transpose. This is a matrix representation of that power in ordinary definition of probability density function of normal distribution. So this is the multi-Gaussian distribution probability mass density function. Okay, now we are going to define the Gaussian mixture model formally. There is nothing. We know a mixture model is a weighted average of individual distributions. That's all. We are going to do that. In the case of Gaussian distribution, the same thing. The ingredients or the sub distributions are all Gaussians, but we are going to find out the mixing coefficient Wi, that weight distribution Wi, in a particular manner. That is the idea. We are going to derive that weight distribution in a particular way to represent this model in a more legible way. That is the idea. Okay, as a first step, the basic assumptions are taken from the k-means background. Okay, in order to understand the Gaussian mixture model, I am using a k-means clustering background. That means we have many data points, but we are only k clusters. We are classify these points into k clusters. My aim is to show that each of these clusters can be determined by a distribution. Here I am going to say that it is a normal distribution. In that way I am developing this model, because this Gaussian distribution can be used to develop our model based clustering. That is one of the application. So this derivation substantiate the use of Gaussian distribution, especially our vector form of Gaussian, to represents a cluster model, a model based cluster. So I use the background of a k-means clustering. Suppose there are k clusters such that in each cluster the data points are normally distributed. That means we automatically have the clusters, and clusters are represented by normal distributions. That's all. It defines a multi-Gaussian distribution with a PDF. As I told you in the previous slide, f of x equal to this expression 1 by 2 pi the whole raised to k by 2 mod sigma raised to half into e raised to minus half x minus mu into sigma raised to minus 1 into x minus mu transpose. This can be represented as n mu sigma. Here mu is the mean vector and sigma is the covariance matrix. Now we are trying to formulate, this is the core part, the mixture as a weighted average individual Gaussians. But we will select some meaningful weight. So this is the highlighted point. We are going to select some meaningful weight instead of Wi in our usual definition. So as a step 2, we define the latent conditional. Latent means some unobserved thing. Now I am starting from a k-means clustering model. That means there are k clusters. There may be some reason, there should be some reason that a particular point belongs to a cluster. That is hidden. That hidden reason is called our latent variable. The presence of latent variable, these data points are classified into different clusters. Okay. Assume that the clustering is due to the influence of some latent variable zk. The zk stands for, that is the reason for a particular data point belongs to kth cluster. We can denote capital Z in vector form. It contains the components z1, z2, etc. zk. It can be interpreted like this. Z2 is the latent sub variable. That is the reason that the particular point, data point capital X belongs to Z2 or the second cluster, like that. Now let us define P of zk is equal to 1 is equal to pi k. It's a very simple notation. We define two things here. Now look into the argument zk is equal to 1. Zk is actually an indicator function. Its value indicate that which cluster the data point belongs. Here zk is equal to 1. That means it gives true value that indicate that that particular data point belongs to kth cluster. Once again I repeat that definition. Zk is an indicator function. If it gives 1, that means the given data point belongs to kth cluster. Now what is this? Probability that zk is equal to 1. That means probability that the given data point belongs to kth cluster. We can interpret like this. I repeat, probability that a given data point belongs to kth cluster is equal to pi k. That means pi k is the probability that a particular data point belongs to kth cluster. Now this pi k is we are going to define this pi k as the mixing coefficient. See, I told you Wi is a weight parameter or mixing coefficient. My aim is to prove that Wi is a probability distribution. Now what is this? Pi k is probability that zk is 1. That means the probability that the given data point belongs to kth cluster is pi k. Now we define a meaningful definition, or we give a meaningful definition to the weight parameter W. It is called the mixing coefficient for Gaussian. Here zk is the indicator function for the kth cluster. Z3 is the indicator function for third cluster, like that. Now what is this? This is the conditional probability. We can interpret like this. A given vector capital X, that means we have an input X, but it has many components. We can think like this. I give an input. That input contains digits from 0 to 9. That means my input is like a strip. It contains 10 digits starting from 0 to 10. That is capital X. So given input, I give an input X. Then probability that for a given data zk is equal to 1. How we can interpret this? A given data point can be clustered into kth cluster. A given data point can be clustered into kth data point. Its probability. That means the probability that a given sample belongs to kth cluster. I repeat, probability that a given data point belongs to kth cluster. We are going to find this. This is my posterior distribution. Once you know the probability for each cluster point, then we choose the cluster with the maximum probability to which that particular vector belongs. That is the idea. We calculate this probability for each cluster. Then I map the data point to which cluster? To that cluster which gives the maximum probability. See, it's very simple. So clustering is in terms of probability, not in terms of actual distance. So P of xn given z, that means a given z, this is our latent variable. P of xn given z means this latent variable leads xn. This latent variable leads xn. The probability that this latent variable, this latent vector affect xn, that is normal distribution. We can interpret like this. We consider a sample point xn. This xn is belongs to nth cluster. What is the reason? There is a latent variable, that is why this xn is belongs to that cluster. So the given z leads xn to the nth cluster. Its probability is actually normal distribution, because each, we have already we said it, each distribution is normal. Each distribution represents normal distribution, and corresponding to each cluster we are going to use this distribution. So P of xn given is a conditional probability. This conditional probability says that this latent variable leads xn to nth cluster, that is denoted by n of xn with the mean mu k and variance sigma k. Remember, this capital sigma is the variance matrix, covariance matrix. Sigma k is the kth element, is the main diagonal, that is the variance corresponding to kth component. So n of xn given mu k sigma k means xn is our data point with the mean mu k and variance sigma k. This is a normal distribution. This is nothing. We simply represent the nth cluster, here nth cluster by a normal distribution. Now we are going to represent using a simple figure. See, I have three clusters. Cluster 1, that is denoted by this red. Cluster 2, that is denoted by this green, and cluster 3 denoted by this blue. This is the real data points. See, this data points red belongs to this cluster because of one latent variable, and also this data points green belongs to this green cluster because of some latent variable, and also for the case of this blue data points. Now I am going to assign each cluster by a respective normal distribution. So the first cluster I assign a red normal, second cluster I assign a green normal, third cluster I assign a blue normal. That is, we define like this normal distribution. Now we are going to the third step. That means we are going to define our Gaussian mixture P of xn. Here we define the component wise definition. Xn is the nth component. P of xn can be defined as the weighted average of individual distribution. Sigma k is equal to 1 to capital K, P of xn by zk into P of xk. P of zk. This P of zk is our mixing coefficient. We know P of zk is equal to 1 is pi k. We are going to use in next step. This P of xn given zk is nothing but the probability distribution under this latent variable zk to the cluster n, that is normal distribution. N of xn given mu k sigma k. Then P of zk is equal to 1, that is pi k. This is nothing but our component xn is defined like this. The probability for xn is defined as the weighted average of normal distribution. This is the real definition of Gaussian mixture. Now we know that xn is only one component. This vector capital X contains n components, and also these components are independent. So we write capital X equal to x1, x2, etc. xn. Then using the independence of data distribution, the probability for this capital X contains n components. This is comma. This comma means it is joint distribution. Joint distribution, we apply multiplication theorem. So probability distribution for x1 into probability distribution for x2 into etc. probability distribution for xn. Into means product form. So n is equal to 1 to, here I use capital N. This n is capital N here, P of xn. But what is P of xn? P of xn is this sum, the weighted average of this normal distribution. I replace this P of xn by this distribution. So what we get, the probability distribution function for this capital X is the vector data point. That vector data point is the product n is equal to 1 to capital N, sigma k is equal to 1 to k, n of xn given mu k sigma k into pi k. This is the probability density function for the Gaussian mixture. So the key point is express each cluster point by normal distribution. Then we directly use the definition of our Gaussian mixture. P of xn is the weighted average of individual distribution into corresponding mixing coefficient. Then we directly use the idea that xn is simply one component. This capital X contained n component. So it's a joint distribution. So to find a P of x, we use joint distribution. In the case of x1, x2, etc., xn, they are independent. So probability for x1, x2, etc., xn. If x1, x2, etc., xn are independent, we can use direct multiplication theorem, and so we apply this product. Now in the product term, the argument of this product contains P of xn. We replace this P of xn by this expression. So we got the probability distribution function for P of x. Look, this product can be considered as a multiple, and the sigma expression is actually a weighted average. Weighted average is actually conditional expectation. So the probability density function or probability distribution for this capital X is product of this one is conditional expectation or marginal expectation. So product of conditional expectation. That is actually the interpretation of this Gaussian mixture model. Probability density function of capital X is product of conditional expectation. The applications in model-based clustering. One of the important use of this Gaussian mixture is develop model-based clustering. So this derivation itself support application of Gaussian mixture model in soft clustering. We can use GMM to find those class to which a particular data point is to be mapped with maximum probability. We find out that probability, then we assign a data point into a cluster in which the probability is maximum. Our aim is to find those class to which the particular data point is to be mapped with the maximum probability. So it is more an inference method than a labeling approach. Instead of giving some labels based on distance, we are developing a probability distribution, and based on this probability distribution we came to some inferences. So mathematically we have to find the maximum probability measure like this. A given sample belongs to kth cluster and its probability. Probability that given sample belongs to kth cluster is equal to P of x given zk is equal to 1 into P of zk is equal to 1 divided by this marginal. We simply take the sum of this numerator. This is nothing but Bayes theorem, the Bayes posterior distribution. So the GMM model can be used to calculate the posterior distribution that help us to develop a model based clustering. Okay, now look into this one. Sigma k is equal to 1 to k, P of x given zk is equal to 1 into P of zk is equal to 1. This is nothing but the marginal. This marginal is also known as evidence. This term, this is a calibration term. This calibration term is used just to ensure that this P of zk is equal to 1 given x is a probability density function. So probability density, it is a probability density function when we take the total or the integral of this, we gives 1. In the place of the sigma we can use integral also. Here the better choice is integration because it's a continuous distribution. It's a continuous distribution. In the case of sigma changes to integral. So I rewrite that expression, but we know that P of x given zk is equal to 1. That means that data point belongs to cluster k, but the kth cluster is represented by the normal distribution n of x given mu k sigma k. P of zk is equal to 1 means probability that that point belongs to kth cluster. Probability for that data point belongs to kth cluster is denoted by the mixing coefficient pi k. So n of x given mu k into sigma k into pi k. The denominator is same, but there is a sigma. So I add sigma k is equal to 1 to k, n of x given mu k into sigma k into pi k. We cannot cancel the terms because this is a sum. First we have to take the sum, then only we simplify. Now I write this expression. This is a posterior distribution. That posterior distribution is gamma of z and k. Gamma of z and k, because it contains summation from 1 to k, and also there are n terms or n components in x. We use the both these ideas in this index, gamma of z and k. This probability is called our expectation measure. We can interpret this gamma of z and k as an expectation measure. To solve the GMM probability optimization, we will use expectation maximization algorithm. In order to find this gamma of z and k, we have to find out this probability. This is the probability that given sample belongs to kth cluster. This parameter can be identified with the help of an optimization method that is called expectation maximization algorithm. Okay, thank you very much.